Right. Cheerios is teaming up with Fitbit for heart healthy choices. But where? Oh, here's the data set. So it looks like maybe calories is your outcome variable, and then you're looking at correlations with that. And wait, hold on a second. Maybe cereal correlation isn't about the data on the outside of the box. Maybe it's about the cereal itself. Let's take a look. So now, does it appear that like the kind of more orangey Cheerios are correlated with the location of the darker brownish Cheerios? I don't really know. That doesn't seem like high correlation there. Um, Sorry guys, I'm kind of stumped on this one. Oh, 1 second, I'm getting a phone call. Yep. Oh, Professor Studeman. Okay, I'm being an idiot. You're watching this and I'm being an idiot. It's not CEREAL correlation. It's oh. Oh, that makes way more sense. Okay. Well, if that's the case, then I think there's only one appropriate thing to do. Whew. All right, guys. So, oops. So today's lecture is about serial correlation, but that is not CEREAL correlation. This is SERIAL correlation. So let's get a little theme music for today's lecture. All right, well, that was a little deep cut podcast joke for those of you that were, still using iTunes back in 2012. The Before I burn out of cereal material, a quick pun about cereals. I want you to ask yourself, what is Snoop Dogg's favorite cereal? The answer is Wheaties. Pretty good, right? Pretty good. I don't I don't hear anyone laughing. That's actually not all that different than when I tell that joke live in class. So, uh, let's go ahead and get started. The This is our last lecture, guys. Very exciting. Um, and so we are talking about serial correlation. This is our last OLS violation, and then after this, it's kind of all eyes on the final project. We've talked about serial correlation before. Like with the other topics that we have uh, covered the last few lectures, multicollinearity and heteroscedasticity, there are actually two types of serial correlation. Oh, I need to add in an extra line there. There's going to be pure and impure serial correlation. Now, when I introduced serial correlation back in as part of the original OLS assumptions, I kind of reminded you that this was akin to assuming that your data are independent. And sure enough, serial correlation occurs when your data are not independent, in particular when they're correlated across time. So if you have time series data, which we'll define in a second, where you're measuring kind of the same object, maybe a stock price one day after another, or attendance at a Dodgers game one game after the next, or people's consumption of toilet paper one day after the next. The data that you get from one day or 1 week or 1 month is going to be correlated with what you get the second month. So when you run a regression on that data, even if you have, say, 52 weeks of data, you don't actually really have 52 independent observations. You probably have a little less data than that, and so we need to account for that in some way, and that's going to be what today's lecture is about. So we're going to start off by kind of just defining serial correlation on our table, which is it's when our error terms are correlated across observations. That's going to be true for both pure and impure serial correlation. And then what are the consequences of it? So the consequences of serial correlation, like with multicollinearity and heteroscedasticity, is bias standard errors. And in the case of impure serial correlation is similar to impure heteroscedasticity in that it is serial correlation that is sort of induced by incorrect functional form. But either case, it results in biased standard errors. And if you have the wrong functional form could actually impact your betas, your slope estimates. So impure serial correlation in that sense might be worse. And we'll go ahead and we'll fill in detection and correction at the end of the lecture, like we've done before. Because this is our kind of third and final standard error violation, kind of coming after heteroscedasticity and multicollinearity, I'm going to go through things fairly quickly because this is going to take the same structure that you've seen before, which is I'm going to define the problem, I'm going to show how we detect it, then I'm going to show how we correct for it, and then I'm going to show you an example in Stata. Serial correlation, the sort of math of understanding what's going wrong, this is the most difficult of the three standard error violations, I think. Understanding the math of serial correlation is trickier than for heteroscedasticity or multicollinearity. Luckily for you guys, you don't have to take a test on this material. You only have to incorporate it into your final project. And so I'm going to go through the math a little more quickly than I normally would, just because I think for most of you, it's not going to be strictly necessary. So serial correlation occurs primarily in time series data. And so what is time series data? Time series data kind of looks like any other data set. It's still, your one observation per row, different variables in different columns. You can run a regression on it. You have an outcome variable and explanatory variables. The main difference is that we use the subscript T rather than the subscript I, because we're denoting that in this case, our data are changing over time. We're observing the same object, but looking at it over multiple periods of time, rather than cross-sectional data, where we kind of observe multiple different people or multiple different businesses at the same period of time. The key distinguishing feature of time series data is that the order of observations are fixed. In other words, it matters in a time series data set which observation is the first one in your data set versus which one is the 17th in your data set. The first one comes first, the 17th one comes 17 periods later. Whether that's 17 days or weeks depends on the specific data at hand. But like if you remember back when you did your survey of students asking them about how much caffeine they drank and how much sleep they got, it does not matter at all what order you ask those people that question in. So long as you have the same 5 data points, the result of your regression is going to be the same regardless of the order. That's not going to be the case in time series data. In time series data, the order of observations is going to matter. The fact that these data are linked over time means potentially that their error term is also linked over time. In other words, something that's sort of unpredictable in one period might have ripple effects. And so if our model isn't accounting for it in one period, it might also not be accounting for it in future periods. This is defined thusly, that the error term in time series data is a function of two things. One, it's a function of kind of new randomness today. Things that just aren't in our model today, that's going to be represented by UT. However, serial correlation is also, or the error term today is also a function of the error term yesterday multiplied by some factor rho. Most of today's lecture is going to be about trying to estimate or understand rho. If rho is equal to 0, then you can say there is no serial correlation. In other words, then today's error term is only a function of kind of the good error, the kind of normal randomness that occurs day to day. If rho is not equal to 0, then there is serial correlation, and so that's why rho is called the term of autocorrelation, or the first order autocorrelation coefficient. Rho tends to be between -1 and +1. Most of the time, though, it's going to be between 0 and +1. When rho is negative, that indicates negative serial correlation, which is kind of an oscillating effect, that if today things were better or above our prediction, then tomorrow they're going to be below what we predict, and then the next day they're going to be back above. What tends to happen more often in time series data is that things sort of stay above what you predict for a little bit. A stock maybe stays above its normal average stock price for a few days or a few weeks and then kind of reverts to the mean, or attendance tends to be higher as a team is doing well and then attendance drops as a team does poorly, but that the sort of correlation is over multiple periods, not bouncing back and forth every period. And when the correlation is kind of over multiple periods, that's going to be represented by a positive row, a row between 0 and 1, that yesterday's error term kind of positively correlates to today's error term. Positive serial correlation, the plot, so notice these graphs, what we're looking at, these are the error terms here. So this is not your outcome. It's the error term and time. And so it tends to be, it's still going to be the case that your error term on average might be equal to 0, but rather than kind of random fluctuations over time, there tends to be sort of a stasis, that if the error term starts above 0, it's going to be above 0 for a number of periods before slowly dripping down below 0, and then it works its way back up, or maybe it looks more like a sine curve, but kind of a slow-moving process of the error term where it stays above or below 0 for long periods of time is kind of a typical feature of time series data, and in particular time series data that has serial correlation. Here's an example of no serial correlation. The residuals, it doesn't look like there's any pattern between between one error term and the one, just after it, just to the right of it. Negative serial correlation, meanwhile, kind of looks like this, where if you're below in one period, then you're above in the next, then below again, then up above, then below, then up above, back and forth, back and forth, back and forth. And so admittedly, the look of negative serial correlation versus no serial correlation is kind of similar. Negative serial correlation is rare enough, and that most of the time, I'm probably going to slip up during this lecture. When I talk about serial correlation, I'm just assuming that we're talking about positive serial correlation. Serial correlation, it doesn't have to just be related to the one period before. It could be, for example, that your error term from 4 periods ago is what is impacting today's error term. You might be saying to yourself, why on earth, if 4 periods ago is impacting today, then surely 4 periods ago impacted 3, which impacted 2, which impacted 1. So that's kind of dumb. Let's just leave it at yesterday's error term. The reason that this might be the case really depends on how the data is measured. For example, a lot of time series data is measured quarterly. So businesses release, say, their financial records each quarter. And if a business, maybe a retail business, tends to do well in the winter quarter around the holiday season, then last year's holiday season might correlate with this year's holiday season, even though that is 4 periods ago. Last year's holiday season might tell you more about what's going to happen this year than last year's fall or this year's fall or something like that. And it could be the case, although we're not going to focus on it in this class, that the serial correlation, that kind of multiple periods are affecting today's error term. We're going to focus on kind of what's called one period or first order autocorrelation, which is just when there's kind of only one row coefficient, not multiple rows. But in advanced econometrics, or in theory, there could be more. Impure serial correlation is serial correlation that is caused by incorrect functional form. Even if the true error, if you had the functional form correct, isn't serially correlated, kind of if you're trying to fit a line to a curve or something like that, you might end up inducing what's called impure serial correlation. The result of it is very similar to pure serial correlation, and kind of our fixes for it are also pretty similar. So obviously, if you have incorrect functional form, you'd like to fix that first, but then with the serial correlation it induces, we're going to kind of do the same thing to it. And so, yeah, here's kind of the standard example of impure serial correlation is if you should have 2 explanatory variables in your model, but you can't collect data on x2 or something like that, so it's omitted. Well, even if the true randomness is kind of random from period to period, what you're going to estimate when you don't include x2 is you're going to have kind of the error term star, where the error term star is the true error plus the other explanatory variable. And so if the other explanatory variable is correlated across time, then you're going to accidentally have serial correlation. So an example of that might be if we want to predict people's consumption of toilet paper, or sorry, I should go up to the top model. If we want to predict people's consumption of toilet paper as a function maybe of the weather and of, let's not get too mean to people with diarrhea. So as a function of the weather, and let's say as some function of the economy, that generally speaking, toilet paper, you buy more of it when you're doing when you're well off. But we can't find data on the economy. So instead, we're just looking at toilet paper as a function of weather. Well, the economy, our x2 variable, it's likely correlated from period to period. Maybe our data is collected monthly or quarterly. There's going to be correlation in the state of the economy from one quarter to the next, and so that correlation in x2 then works the same way as if you had correlation, pure serial correlation, as if last period's error term was impacting today. And this is, now I could have skipped this slide, that's similar. All right, and so here you see kind of the idea of impure serial correlation visually, which is if the functional form, if the true relationship between x and y maybe should be like a logged relationship or a polynomial relationship, where the true relationship is kind of this curve shape, but we don't specify that correctly. Instead, we say, no, we're fitting a line to this curve. The best fit line looks like what you see on the graph, but so then automatically, kind of all of these residuals towards the middle, they're all automatically negative, not because actually all the periods in the middle had negative randomness, but just because we kind of fit the wrong model to the data. We've kind of automatically forced serial correlation. Now, in the middle, our errors are negative. Towards the left and right, our errors are positive, but not because there's actual serial correlation. As I kind of said at the lead, the consequences of serial correlation is that it doesn't bias your beta hat coefficients, it screws up your standard errors. And between this multicollinearity and heteroscedasticity, serial correlation screws up your standard errors worse than either of those. It's kind of the biggest issue. Again, it's mainly prevalent in time series data, so most of you aren't going to have to worry about it, but if you do have time series data, it's absolutely critical that you account for serial correlation. The way that we detect serial correlation is using the Durbin-Watson test. The Durbin-Watson test so it's first order in nature, so kind of by default, we're just going to be assuming that it is last period's error term that impacts this period. And assumption 3, I'm skipping that, so don't worry too much about it. It assumes that you have an intercept term. We always have an intercept term, so the only real assumption that we're making in this case is that the serial correlation is first order. In other words, that there's just one, that yesterday's error term is the only one impacting today's error term. There are other tests for other sorts of serial correlation, but Durbin-Watson is going to serve our purposes. The way that the Durbin-Watson stat works, so this equation I know looks a little thorny, but let's kind of dive into it. It is a statistic that takes the residuals from a regression. So what you do with time series data is you run a regression just like normal. And so the regression is going to minimize the sum of squared residuals. It's going to find the best fit slopes for the independent and the outcome variables. And you can then calculate the residuals from that regression. And when you do that, you can then take those residuals and calculate the Durbin-Watson statistic. In particular, what you're going to do is your denominator is each residual squared. So this is essentially the sum of squared residuals in the denominator. In the numerator, you are taking the difference between today's residual and the residual from the period before that. The numerator summation starts at 2 because you can't take the difference for the very first residual. You kind of have to start at the second one because the first residual, the earliest data point in your data set, you don't know what the residual was for the period before. If we think about this, if there is strong serial correlation in our data, then today's residual is usually going to be pretty similar to yesterday's residual. What that's going to mean is that the whole numerator in the sum, each of these terms is going to be relatively small because you're subtracting two numbers that are pretty similar from each other. And so if the numerator is pretty small relative to the denominator, everything's going to be positive because everything's squared. But so if there is serial correlation, the numerator is going to be small, and that's going to mean that the statistic is relatively close to 0. If there's extreme negative serial correlation, then today's error term, if today's error term is like positive 2, then we're expecting yesterday's error term to be like -2. That, in other words, the difference between today's error term and yesterday's error term is going to kind of be twice the magnitude of today's error term. So 3 versus -3, or 0.6 versus -0.6, or -0.4 versus 0.4. If you kind of subtract a number from its negative counterpart, you get twice that number. And so if that's the case, if the numerator on average is twice as big as the denominator, kind of each term in the numerator, then that's going to end up, the numerator is going to end up being 4 times larger than the denominator. So in the extreme, if we get a Durbin-Watson stat of 0, that's extreme positive serial correlation. If we get a Durbin-Watson stat close to 4, that's extreme negative correlation. And if we get a Durbin-Watson stat around 2, then that's roughly going to be what you would expect if there's no serial correlation. Oops, need to get rid of the annotation. So the Durbin-Watson test is going to be a little unique because we're actually going to involve 2 numbers. There's going to be kind of a lower bound and an upper bound, where if the Durbin-Watson test falls in between those two, the result of the Durbin-Watson test is going to be inconclusive. In other words, we're not going to be confident enough to say that there's no serial correlation, but we're also not going to be confident enough to say that there is positive or that there's negative serial correlation. So the default null hypothesis for a Durbin-Watson test is that the rho value is less than or equal to 0. This is kind of the default. What we're testing for is positive serial correlation. You're going to kind of notice from now on that the word negative serial correlation doesn't really appear here, because most positive serial correlation is just so much more common. So here's our null hypothesis, is that rho is less than or equal to 0. Really what we're focused on is that rho is equal to 0, that there's no positive serial correlation. And our alternative, kind of what we might be looking to reject, is that there is positive serial correlation, which is represented by rho being above 0. The way the Durbin-Watson test works, oh, and I should have pulled open that table. I'm going to have to do that. Maybe I can do that while I'm blabbing on a separate screen. So the Durbin-Watson test is going to give you 2 values, a lower bound and an upper bound. The lower bound is DL, the upper bound is DU. If the Durbin-Watson test is less than DL, that's going to mean that your Durbin-Watson statistic is close to 0. Close to 0 means high positive serial correlation. And so that's going to be representative of, oops, here comes, oh no, that doesn't have the table on it. Does it? Shoot. Sorry, this is boomer level technology use. It's probably on Moodle. I'm not sure in my own file, and I can't pause and record this and stop recording this thing. So here we go. All right. Let's take a look. So here's what the Durbin-Watson table looks like. It's the same one. This is the table from your textbook. So K is going to be the number of explanatory variables in our model. N is the number of observations in our model. So that's going to work as per usual. And what you're going to do is, for a given sample size, let's say we have 30 people in our sample and 5 explanatory variables, you're going to kind of go down the rows, across the columns, and so let's say your critical values are 1.07 and 1.83. 1.07, that's going to be your DL, your lower bound, and 1.83, that's going to be your upper bound. When you calculate the Durbin-Watson statistic, if you get a number below 1.07, you're going to claim that there is positive serial correlation. If you get a number greater than 1.83, you're going to say there is no serial correlation, or we fail to reject no serial correlation. And if you get a number in between those two, you're going to say your test is inconclusive, and you just can't say either way. So that's just kind of a repeat of that. So I'll wait. So now let's also talk about kind of our remedy for serial correlation. In this class, in the textbook, there are 2 remedies. In this class, I'm only going to talk to you about the first one, generalized least squares. That line got out of hand quickly. The generalized least squares is maybe the hardest mathematical thing that we do in this class, and I'm going to kind of focus on the math fairly quickly. But if you want to understand this, especially if you're doing time series data with your final project, I'd encourage you to kind of pause this video at times, really kind of take the math that's on these slides and write it down yourself, kind of work through it on your own, and I think it'll start to make sense. The idea of generalized least squares is that this is the equation that we initially start with, but if there's serial correlation, then we end up with equation 9.19. In other words, we substitute into the error term kind of the definition of serial correlation, that today's error term is a function of yesterday's error term multiplied by rho plus ut. What we want to do is we want to transform this equation into a regression that we can still run, where we still have some outcome variable on the right and some explanatory variables, on the left, and some explanatory variables on the right, but where the error term in that transformed equation does not have serial correlation. That's what kind of the math that I'm about to do is geared towards. The way we're going to do that is we're going to think about yesterday's data point. So if this is the definition of today's data point, that today's outcome is a function of an intercept plus beta 1 times today's x1 plus rho times yesterday's error term plus ut, then it's also going to be the case that yesterday's data point is a function of the intercept plus beta 1 times yesterday's data point plus yesterday's error term. And what I've done in equation 920 is I've just multiplied the entire equation by rho. So maybe a better way of saying this is I've taken equation 9.18, today's equation. I've just rewritten 9.18 for yesterday, and then I've multiplied both the left and the right side by rho. So now what we have, and essentially what this math is going to be, and followed by a lot of algebra, is I'm going to solve equation 9.20 for rho times epsilon t minus 1. I'm going to get this alone by subtracting this other stuff over to the left-hand side, and then I'm going to plug all of this in to equation 9.19. And then I'm going to have to kind of do some algebra to simplify things and solve for terms, but in a general sense, when I plug this into equation 9.19, now everything in equation 9.19 is either ut, which is kind of the good sort of error, the purely random, only matters for today error term, or things that we either know or want to estimate. So the only things left are the good error, ut, data, like x1 t minus 1 or x1 t, which we know what the values of the data are, or the coefficients that I want to estimate, beta 0 and beta 1. So here's the equation after I've plugged it in and then simplified the terms a little bit. And so the way it gets rewritten is instead of an outcome as a function of the intercept times the explanatory variable, is you can rewrite it as the difference in outcome from yesterday to today discounted by rho is a function of the intercept discounted by rho plus the impact of a 1 unit increase on x1 multiplied by the difference between yesterday and today. Let's see, I'll switch colors. These things in red, y minus yt minus 1 and x minus xt minus 1, we can actually calculate those if we have an estimate of rho. If you knew that rho was, say, 0.2, then you could go in your data and you could say, all right, well, today the weather was 80 degrees. Yesterday the weather was 76 degrees. 80 minus 0.2 times 76 is some number. You could kind of calculate this. And importantly, beta 1 in this equation is not it's not being multiplied, well, it still stands on its own. In other words, if this variable, which we're going to call x1 star, right? This thing that we can calculate, we're going to treat that as a new independent variable. So rather than just the weather today, we might think of it as the difference in weather between yesterday and today, but that's a number we can calculate. And so this equation can be rewritten like we have here in 9.22, and importantly, beta 1 is unchanged. So if we're able to estimate the regression in 9.22, we still get a valid estimate of beta 1. So our slope coefficient is still unbiased, it's still the best estimate, and all these things. So we did some kind of fancy math, but in the end, what we have is a slope estimate that we can still rely on. To estimate this equation, though, we need an estimate of rho, and that's where this fix is going to come in, is we kind of have to figure out what rho is in order to estimate equation 9.22. The way we're going to do that is we're going to start by assuming that rho equals 0. We're going to start by just running the regression. Then we're going to look at the serial correlation in that regression when we assumed no serial correlation. We're going to see, are our errors kind of correlated with each other? And if they are, how strongly correlated are they? If they're, say, maybe 0.4 correlated with each other, then we're going to rerun this equation, but we're going to assume that rho equals 0.4. And then we're going to look at that result, and we're going to say, all right, in this new equation, how correlated are these errors? Are they more correlated, less correlated than before? If they're less correlated before, how strongly correlated? And we're going to plug in and kind of iterate and keep trying to guess different values of rho until we have a model with no serial correlation. So this is saying that kind of this good equation, equation 9.22. In that equation, the error term is not serially correlated. All we have in this equation is ut, and the slope is an unbiased true version of the slope that we're interested in. The adjusted R squared of the two models is not comparable. So when we do this form, we're not really going to have a sense of how well our data fit the model because this transformation kind of screws up with our typical version of adjusted R squared. The name for this method that we're doing is called generalized least squares, GLS. It's been at the top of the slides. And in particular, we're doing what's called the Praise-Winston method. The reason this is mostly important is because the command in Stata is going to be called praise. So rather than typing regress and then your y and x variable, you're going to type praise and then your x and y, or your y and x variable. So again, the way the Praise-Winston method works, kind of now focusing on what happens to the error term, is you run the OLS regression, then you regress your residuals on each other, and you estimate rho, and you'll get a rho hat. Think in this case of rho kind of like a beta coefficient, where one error term is your outcome variable, yesterday's error term is your independent variable. You estimate the relationship between yesterday's error and today's error, and you get rho hat. Then you plug rho hat into the equation 9.21 from the slide before, and you'll get new residuals and new error terms, and you kind of repeat the method until rho hat kind of stops changing. Eventually, this process is going to converge. So here, well, I think we're going to do the chicken demand model in class on Tuesday or Thursday, but kind of a sense of what happens when you do this. You start out by running OLS and you'll get some set of results. Then when you do the GLS, your coefficients might be slightly different. So like 0.11 goes down to 0.08. 0.03 becomes 0.016, so it kind of got cut in half. But what's going to be really different are your t-statistics and your standard errors. So this t-statistic gets more than cut in half. This one, I guess in this model doesn't actually change all that much. So maybe this was a model with a low serial correlation to begin with. So I've planned an example actually in Stata, so I apologize. That slide was not, I thought I had deleted that slide. So let's go ahead and look at this in Stata. Okay, so we're going to start off here. This is a quick example of no serial correlation. This is the restaurant data set. This is with the different Denny's restaurants. There's no serial correlation. It does not matter in this data set which restaurant is listed second versus fifth versus eighth. It's kind of each one is just an individual restaurant. And so we're going to see that by, Let's do a regression of sales at the restaurant on income, competition, and population, our kind of normal model for restaurant sales. Then I'll predict the residuals. And then I'm going to graph the residuals against, say, income. So two-way line E income. So it seems fairly clear here that the residual from one period does not have much correlation with the residual from the following period. It's kind of equally likely. I'm drawing a blue line here at 0. Kind of most of the time the residual switches from above to below 0, but some of the time you get multiple periods below 0, or maybe multiple periods above 0. And it's essentially random whether the residual is staying positive, going negative, lack of correlation. This is what non-serially correlated data looks like. The other data set I have in mind that I used earlier on in class is the James Bond data set. We've talked about this one a couple times. So here, my data, again, is kind of for each movie. You have the gross income of the movie, the budget of the movie, the rating of the movie, also the actor of the movie. But importantly, these movies came out in order. So Dr. No came out before Russia with Love, which came out before Goldfinger, but there's a natural ordering to the James Bond movies. I'll just kind of restart the data set. And so the way that you deal with time series data in Stata is the first thing is Stata, remember that Stata is stupid. Stata will do what you tell it to, but it doesn't figure things out on its own. So if you don't tell Stata that this is time series data, it won't know. So to tell Stata that this is time series data, we have to tell it which variable is the time series variable. And so in this case, the time series variable is year released. So we're going to do the command ts set year released. And that's TS stands for time series, and set means set the time series variable. So year. No, I was spelling released wrong. All right, so now Stata knows that, okay, these observations are ordered based on this variable year released. Seems like you shouldn't have to tell Stata that, but you do. Now, if we run a regression of, let's say, the gross income that a movie makes on its budget and its rating, we get that the more money that is spent on a movie, the more money it makes. The higher the rating of the movie, the more money it makes. And so those coefficients should be unbiased and everything, but it's possible that there's zero correlation in our data. And so let's look at the residuals. So I'll predict the residuals, predict E, resid, and then I'll graph E and the year. Oops, I need to tell Stata what kind of graph. All right, and so here's our 0 line. So I know this might not look super different from the graph before, but you'll notice that in this James Bond data, we have some sustained periods of positive residuals and some sustained periods of negative residuals, much more than you would expect if there was no correlation. So from kind of all of the James Bond movies from 1980, pretty much until Daniel Craig took over, these all made less money than you would predict based on kind of the characteristics of the movie. Whereas in the 1970s, we have 4 or 5 movies here that all made more money than you would predict, based on kind of the demographics or the explanatory variables for the movie. And so for what is, I believe, like 23 or 24 different data points, we only cross 0 1, 2, 3, 4, 5 times. The residual does seem to correlate between one period and the next. I just do DW Durbin. I forget my own command. There we go. So now, to test for serial correlation in the data, you do estat Durbin, and you get your coefficient. Or is it DW? Okay, sorry. The correct command, Durbin came up with multiple tests, is we want the Durbin-Watson stat. So the Durbin-Watson statistic, our D statistic in this case, is 0.3935. So we have 3 explanatory variables, we have 23 observations, and so we would then go to our Durbin-Watson table and go 23 observations, K is 3, our lower bound is 1.08, our statistic is 0.39, that is well below 1.08, so this would be a situation where we reject the null hypothesis of no serial correlation in favor of serial correlation. This statistic is low enough, in other words, our residuals are correlated enough with each other so that we can be statistically confident that there is serial correlation in the data. And so then what do we do to fix it? Well, we're just going to run the same model, adjusted gross, adjusted budget, average rating. But we're going to use the praise command. And so you'll notice that what happens when you run the praise command is Stata starts out by assuming that rho is 0. It assumes that there's no serial correlation. And then it looked at the kind of correlation between the residuals after it kind of ran OLS. And the correlation between those residuals is 0.35. And so now it took that 0.35 and it essentially plugged it in to this equation, and it generated X star and Y star, and it reran the regression using a rho hat of 0.35. And when it did that, its new rho hat was 0.36. Plugged that in, got 0.3688, 3689, 8989. And at this point, once it's kind of converged to, I think, like 7 or 8 decimal points, it's confident, all right, the true rho, the true serial correlation in this data is 0.3689. What that means is if we estimate equation 9.22 with a rho of 0.3689, we have removed the serial correlation in that data. The only thing left in this equation is the true random error from day to day. We've removed the kind of dependent part of the error. And so the results from this model should be consistent, unbiased, and the standard errors will be correct. They will be free of serial correlation. So our standard errors aren't actually all that different here from before. So both kind of examples I've given, I haven't quite shown the drastic importance of serial correlation, but we've gone from 0.62, or sorry, standard of 0.626 and 55,000, whereas before it had been a little lower and a little lower. Beforehand, we had been underestimating the variance in our model. Low standard errors, remember, relates to higher t statistics, and so without adjusting for serial correlation, we may have claimed that things were statistically significant when they weren't. Yeah, so that's just kind of a quick and dirty of how to apply serial correlation, kind of the Stata code. We're going to practice this in our lab on Tuesday and Thursday, but I think that's it for my overview of serial correlation. Look forward to a couple more corny serial jokes coming your way on Tuesday and Thursday. But other than that, I think I'm going to sign off. This should be my last lecture on my own. So thank you guys for listening, and I will. I guess I'll go finish my bowl of cereal that's been sitting there for 40 minutes, and I'll see you guys in class soon. Take care.